Select the major product of the following reaction. And so we want to look at what we are reacting together here in order to determine the reaction pathway. So we have a secondary alkyl halide, and we are reacting this with methoxide, which is a strong small base. Strong base, and it's also a small base. Okay. And so this combination of a secondary alkyl halide and a strong small base will tend to give us an E2 reaction to form the most stable alkene product that is possible. The other detail that we are given here is heat, and you might have noticed this. I forgot to mention it on the other videos, but heating the reaction up just tends to push the reaction a little bit more into the E2 direction rather than SN2, although this would probably still give elimination even without the heat. That just makes it faster. Okay, so going back to the point about the most stable alkene possible. The word possible is important because we've got some constraints in an E2 reaction. The hydrogen that we remove needs to be 180 degrees away from the leaving group, or else the reaction doesn't work. And our substrate here is a cyclohexane ring. So we need to know that that's not flat. It exists in a chair conformation. And so here is a cyclohexane chair. The only way to have groups 180 degrees apart on the chair is if they are both axial. So I am going to draw the iodine on the axial bond. This methyl group here is pointing in the opposite direction. So the iodine is pointing up. That means that the methyl group is pointing down. So I have a methyl group here at this axial position. And so I also have hydrogen. And ideally, I would form an alkene here because that would be the most stable alkene. However, we said it's the most stable alkene possible. We can't take that hydrogen because it's not 180 degrees away from the leaving group. And so we need to take a hydrogen from this adjacent carbon atom instead. On that carbon atom, we have two hydrogens, one that is equatorial and one that is axial. And so that axial hydrogen is facing in the opposite direction. Okay, so we took and drew a chair structure here. You might be wondering, well, on an exam, if I don't have a lot of time, do I need to draw a chair structure? No, and I wouldn't, frankly. I would recognize that I need this 180 degrees apart, which on a cyclohexane ring means that halogen and the hydrogen need to have a trans relationship, one pointing up and one pointing down. And we can see that even without drawing out the chair structure. So what I would notice here is that the methyl group is going into the plane of the page, so the hydrogen is not. And we can say, okay, that's not trans to the iodine. And that tells us then we have to go to the other beta carbon atom where we do have a hydrogen that is trans. And the methoxide could remove that hydrogen. These electrons swing in to form a double bond and we lose the leaving group. And so that gives us as a product an alkene. We've lost that. And then one carbon atom over, we have the methyl group. Nothing happened to this center, so the methyl group should still be pointing away from us as it was. And this is option A.